In this second video, we want to look exclusively at the inner products for vector spaces. And we're going to define the inner product, and you can see that orange label, so this is a definition that you want to know. It's going to be denoted by a bracket, okay? A bracket, left bracket u comma v, right bracket. That's the inner product of u and v. Okay, and it's going to be a function that maps the Cartesian product of a vector space with itself to a field, not necessarily the reals. And it has to satisfy three conditions. So the first condition it has to satisfy is that it has conjugate symmetry, meaning that when we change the order in the inner product, we have to take the complex conjugate. Obviously, if we're working with real vectors, it's purely symmetric. In other words, it's when we change the order, we get the same result. Okay? It's positive definite, which means that if u is 0, the inner product of u with itself is 0. Otherwise, the inner product of any non-zero vector with itself is always greater than 0. Okay? And that's what positive definite means. It's a function such that when we look at any vector, if the vector is non-zero, it has to return a positive value. That's what positive definite means. And it's linear in its first argument. And what that means is that if we take the inner product of a linear combination with a vector, basically that vector distributes over the left linear combination and the scalars factor out. If this was complex, we have to be careful because it's not linear in the second argument, although if it's real, it is. Now, we normally think of a dot product, which is just a special type of inner product. It's not the same as an inner product. And so we're going to define that as basically a function that maps any two vectors to the sum of the product of its like components. And we know that there's a relationship actually between the Euclidean norm that we just talked about and the dot product. And if we look at the definition of the norm of v for a real vector in Rn, it's the sum of the square of the components. But if we look at the inner product, we can see that the sum of the squares of the components is a dot product of v with itself. So it's a square root of the inner product of v with itself. And the way we normally express that is we say that the square of the norm, or the square of the length, is equal to the inner product of the vector with itself. Now there are a couple of really important facts about dot products. So the first is what we call the Koshi-Schwarz inequality. And I'm only going to state it for vectors in Rn. And the theorem says that if we have two vectors in Rn, the absolute value of their dot product is always less than the product of their lengths. And I want to prove this. This is such an important result that it really bears proving. So let's go ahead and start off with the expression for the sum of the squares of the lengths. This follows just the definition of norm in a Euclidean n space. And now I'm going to go ahead, I'm just going to distribute the right-hand side. And you notice I'm going to get two terms. I'm going to get like terms where u and j have the same, where u and v, sorry, have the same indices. These are my like terms. And I'm also going to have cross terms. Okay. Notice how I'm doing the indexing. I is starting at 1 and going to n minus 1. J is starting at I plus 1 and going to n, so that I and j can never be the same, but I take into account all the possibilities. And I'm going to group u and v components where the indices are swapped. Okay, so this might be u1, v3, u3, v1. They always come in pairs like this. Okay? And now I'm going to use the fact that the sum of two squares is always greater than or equal to twice the product of those quantities being squared. And that's going to give me the following inequality. Basically, I'm going to replace this by twice the product of all of these components to the first power. Okay. But I'm going to notice now that the right-hand side is just the square of the inner product, right? I'm getting the like terms, the square of the like terms, and I'm also getting all of the cross terms. And so I can simply replace that entire side by this, and that suffices to prove the theorem. And there are other theorems. There are other proofs of this theorem, by the way. You can go online. There are some really nice proofs. But this is the most direct algebraic one, I think. Okay. We want to talk next about direction cosines. And so we're going to notice something interesting, that if we go back and we rewrite the Cauchy-Schwarz inequality by just dividing through this whole inequality by the norm of u and the norm of v, notice that u divided by its length, that's what the norm is the unit vector. So we're saying that the unit vector of u dot product with the unit vector of v always has a magnitude between 0 and 1. And that kind of looks like a trig function, right? So this suggests that we define the inner product of any two unit vectors as the cosine of the angle between them. We call this the direction cosine, okay? And so this is the picture, that we have u and v, the angle between them, and this inner product is actually equal to the cosine of this physical angle. Proving that is a little tricky. Okay, I mean, we can obviously show this is true in R2 and R3. In higher dimensions, it's a little trickier. We have a lot of intuition to suggest it's true. For example, when v is equal to u, okay, we know that the inner product of a unit vector with itself is 1, which would imply that the angle between the vector with itself is 0. That makes sense. What's not so easy is showing that when they're orthogonal, they're actually perpendicular, the inner product always gives us 0. Okay, but it is true. We're just going to accept this as a fact. Okay, given all of this, we want to talk about something that's a very important application of direction cosines and dot products, which is called a projection of a vector onto another vector. So we noticed something interesting. We just showed that u and v are orthogonal if and only if the angle between them is 90 degrees. Well, that's the definition of orthogonal. Of course, that's true if and only if the cosine of the angle between them is 0, which is true if and only if the dot product of the two vectors is 0. So notice now that we have an algebraic condition for two vectors being orthogonal. Notice that this dot product is an algebraic quantity, right? We compute it as a sum of the product of, the like components, right? This is a formula. So rather than just having a purely geometric way, we now have an algebraic way. Now we note something interesting. If we take the dot product of u with the unit vector of v, okay, we find out that we have the product of their length times their direction cosine, and of course the length of a unit vector, in this case v, is 1, so we end up getting this. All right. Now let's look at a second what that is geometrically. Okay, so here's our vectors u and the unit vector v, and we know straightforward from geometry that the length of u times the direction cosine is just basically the length of this line segment when we project u onto v. We drop a perpendicular down, right? And this is going to be the length of u times the cosine of the angle between them. And notice I can make that into a vector. Okay, this is a length, but if I multiply by the unit vector, v, this basically gives us a vector. And so now we've kind of decomposed u. There's a part of u that's along v. We call this u parallel v. Okay. That's the projection of u along v hat. Okay? What's equally important is that if we look at the rest of the vector, notice I can do vector addition, right? U is equal to the sum of this vector plus this vector. Well, this vector here is just going to be u minus the projection of u along v hat. and this is perpendicular to V. Okay, and we can actually prove that if we take the inner product of this with V hat, we should get 0. And I would urge you to do that if it's not obvious. Okay. What's really important is that we notice that we can decompose a vector given another vector. So if we have two vectors u and v, we can write u as the part of u that's along v and the part of u that's perpendicular to v. This is a way of kind of decomposing a vector into orthogonal components. And we're going to actually generalize this when we talk about subspaces. Okay, for example, if we have a vector in R3, we could actually project it down into the xy plane, right? Not just projecting onto a vector, but onto actually a plane. And we could do the same sort of decomposition. And we're going to show how that's done in a more general way in one of the upcoming vectors and one of the upcoming videos.